almost everybody that I knew prior to coming to CppCon has had nothing but good things to say about the conference and the quality of individuals that you'll see around here. Just try and take the plunge one year. You'll learn something 100% guaranteed.
All right, welcome. My name is Michael Caisse, and having some problems with the computer not playing along nicely with the video setup here. And thank you, Simon, for lending me your computer, which was awesome, but doesn't have all my normal stuff on it. So we'll see how this works out. The irony of this is years ago, I had a Linux machine, and it didn't work well with the projector. Actually, the projector was broken, but everybody blamed my Linux machine, right? And so when I had to buy new hardware, I'm like, I'm buying a Mac because nobody ever blames the Mac, right? Yeah, I don't know. Okay, we're going to talk today about EtherCAT and really about some strategies to use to integrate C libraries with your C++. Some of that. We'll see how this talk goes as far as what we get involved in and where it goes. But just as a show of hands, how many of you deal in an embedded world of some sort? Whatever you want to call embedded, right? Okay, excellent, great. So EtherCAT is a technology that, this will be hard without my pointer that is hooked up to my thing on my other laptop. Everything's falling apart now. EtherCAT is a technology that allows industrial systems to communicate to one another. It's a system that, so some of the problems with communications in industrial systems is that you need deterministic communication. You need to know what's going on. You kind of want it to be, well, relatively fast, right? Can't be too slow. And topologies are always kind of interesting. And EtherCAT supports a variety of different topologies. On the screen, you can see that we've got some things that are branching off. We've got things that start looking like ladders and trees. And it's able to handle all these different types of topologies. The beauty of EtherCAT, part of the beauty of EtherCAT, is that you can use Ethernet type stuff to make it all work. And so it's relatively inexpensive. And with that, because they've spent some good time on this, they're able to do a variety of different interesting things. Ciere joined the EtherCAT technology group earlier this year as a member. And so I'm just going to borrow some of their slides because it'll make this easier. In particular, this little video here helps describe how EtherCAT works. So let's go ahead and just start this playing. All right, so if you think about how Ethernet normally works, Ethernet, you're sending multiple packets out at a time to destinations, right? Packets are going, they have some place that they're supposed to end up at. How EtherCAT works is a packet has a payload that is for everybody, has portions of the payload that are in the packet for each of the slaves that are on the string. And so they know where to pull information out and where to put information in. It's part of the setup process for this. And so as that loops through, that data packet loops through, you can see they're pulling out the information that they want, and they're putting their information that needs to be delivered back in. As a result, it's a packet, it's one. And it creates then this thing that's fairly efficient, but it also creates something that's going to be deterministic. The master is able to determine how long a cycle time is. Is going to be able to figure out what that cycle takes. Yeah?
Is it a coincidence that there is enough space in the ring when once the packet arrives at slave 4 after slave 3
Yeah. Yeah.
Coincidence or is it planned?
So the question is it coincidence that there's just enough room in the right spots for things to get put back and forth? It's planned. So there is a negotiation that occurs at the beginning and some amount of, I've set my system up. I know the things that are out there. And the packet size is determined, as well as the addresses in which each of the slaves will be able to get information and put information. And you can see as this little video was running, they're not necessarily doing it in contiguous space, right? They're pulling things out wherever it happens to be available. And that's this negotiation process that occurs at the very beginning of the setup of the network. So there is a plan behind it. It's not just happened. Yeah, so there's a negotiation that's occurring for this to happen. Good question. All right, so you can see that we have the straight line, and then off of slave 2, it branched off, and you have like another node of slaves that are kind of branching off slave 2. And we at least think about the data running in a cyclic manner. We're not going to get into EtherCAT in heavy-duty detail or anything, but really there's a cycle that's in flight, and we know how long that cycle is going to occur. And so as long as everything has been planned well enough, you know that what your cycle time is, basically, right? And so your cycle time is interesting. It tells you how fast you're going to be able to put out new data. But that doesn't help necessarily with the synchronization of all the slaves, right? So each of the devices have received data, but in a industrial size system, maybe you're in a paper mill or something of that sort, it would be nice if the cutter actually cut at the correct time, not just cut, right? And so cycle times are usually measured in about 100 microseconds for a cycle. So that's about the range of a cycle. But the other part of the problem is, how are we going to synchronize all the clocks? And so there is distributed clock mechanism inside of EtherCAT. If you do not pick a distributed clock master, one will be picked for you, and it then becomes the time master inside of the network. There is a process in which all the other slaves that care about distributed clocks will go ahead and synchronize their clocks and find their time. You can also add in like a grandmaster clock. So if you have a grandmaster clock, a clocking system, you can go ahead and stick that in, and that will become the master clock. The advantage of doing that, a grandmaster is usually GPS synced, and you now can have devices or plants or areas that are not co-located that are actually synchronized with one another properly. So what occurs inside of this type of a synchronized system is once everybody's on the same clock, then you have your distributed clocks are synchronized. They continue to update, and if the current master clock becomes bad, then another one will get voted in. They've got all that type of stuff built in. This diagram kind of gives us an idea of why we want to do distributed clock synchronization. So EtherCAT uses a signal system called sync 0 and sync 1. Those are just 2 pins that came out of the original ASIC device that they have, which are kind of like what's going on at any particular time. And so they just continue to use that terminology. Sync 0, we can set up the system using the sync 0 type synchronization that you can see that outputs valid marcation. That is controlled then by sync 0. And all devices, their sync 0 output valid will occur at the same time. And so the distributed clock allows us to bring data in, so the data is moved around through and shifted into the different devices, and then the devices act upon the data that's been shifted into the device all at the same time. So they step at the exact same time. And so the DC allows us then to keep here it's called the outputs because it's based upon the master's point of view. So those are our inputs as a slave device. we can then go ahead and act upon that data when we're supposed to act upon it. There's another slightly more complicated setup in which you can have synchronization that occurs on the inputs for it, as well as the synchronization of when to sample data that you might be sending back to the master. And that's what that sync1 signal is. So we're not going to get much more into EtherCAT, too much more. The technology is very cool, I think. It's very cool. I've kind of been on the outskirts and using it in and out for about 3 years now. And this year ended up with a project I had to really like dig into it and actually use it for realsies, not just as a user. So the DC allows us to achieve system-wide jitter of less than 1 microsecond, far less than 1 microsecond. And so in most industrial control systems, that's plenty fine, right? You're happy to have it. And the things that we were doing were fairly tight, and this provided exactly what we needed for a solution. And so that's what we're going to get from this system. So the project that I'm alluding to that occurred at the beginning of the year was a complete research project. The outcome of it was going to be a bunch of white papers, but to get to the white papers, we had to do proof of concepts and actually have a real thing working and demonstrate to some extent to get buy-in and credibility that the thing was what it was supposed to be. How many of you love to write throwaway code? Nobody. What a shock. There, one. We got one. What do you like, really, or do you like to write throwaway code? Yeah. Yeah, no, right. There doesn't have to be any pressure. There doesn't have to be any pressure. So we spend a lot of time as engineers feeling very, very uncomfortable with things that we call technical debt, right? It just hurts inside, right? It's horrible. So part of my job, one of the hats I wear is an engineer hat. But another hat that I have to wear a lot is the business person hat. And businesses don't exist to write perfect code. They exist to make money and produce products. Now sometimes, in fact very often, those are related. Usually inversely related, by the way, right? When something bad happens, you lose money, not necessarily because something good happened, you make money. But you would like to think that they're more closely related. But as engineers, we don't like that idea that we're just like throw something away. And here's the philosophy problem. When you're trying to just put something together, and you're trying to do an R&D project, solely a research project, that the outcome is a white paper and you're never going to see the code again, you should not get too attached to it, right? And in this project, there were some really, really hard problems to solve. And EtherCAT wasn't one of them. It happened to be a problem for us to solve because hadn't done it yet before at this scale like this. And so it was a problem, but it wasn't the problem. Right? It was just part of the thing that built the solution for the final thing that the customer wanted. So here, I've got a question for you, all right? This is a Spark Fun JetBot. Let's say I handed each of you a Spark Fun JetBot right now. I just like pulled them out of the bag, I walked around, and I gave everybody one of them. And I said, you have exactly 2 hours to put together code so that the bot drives around. It could be random, I don't care. It just drives around, and when it detects my face, it stops. And then it spins around circles. Okay, that's it. That's what you have to do. All right? Ready, set, go. How are you going to approach this problem? It's a Jetson Nano. It's quite capable. There's a camera on the front. Okay, so the hardest part seems like facial recognition. Okay. All right, I might try to figure out facial recognition because that's going to sound hard. Yeah. Okay, yeah. Ben is going to fake the face detection. In fact, as I was saying this, I was thinking I might probably try to fake the face detection too. And like just detect a blob or anything at all and then just start spinning around and hope that I got it, right? Okay, that sounds reasonable, I guess. Yeah, so if that's allowed, I didn't say you couldn't use a remote control. Yep, right, all right, yep. Yeah, any other thoughts?
I think many of these modules are ready. For example, facial recognition and something like that. Just I think that having a big picture is enough. For example, have a loop and first doing that, second doing that. If this happens, second, for example, then doing that.
Okay.
Facial recognition and something like that. I don't think that's a problem.
Okay. All right. So one suggestion is that facial recognition might not be a problem. There might be a way to do that, and so we just had to figure out the control loop itself. Maybe?
Just the rules.
The rules. Oh, the rules.
For example, stop if you recognize me.
Okay. All right. Did you have something? No. Okay. All right. All right. Okay, so it ends up that facial recognition is something that's already solved by this thing. It's not that so bad. The beginning of the year, Simon and I took the Mark Rober engineering class. And if you don't know who Mark Rober is, he's like some YouTube star or something guy, right? He's the squirrel dude. Okay, so what was interesting about this is we had to do 3 builds during the class. And you would get the assignment of what you had to brainstorm about, and 1 week later you had to have the video for it, right? And unfortunately I'm an overachiever, so, and my son is no better. And at the beginning we would always pick something too hard. But you would realize, like, I don't have to write perfect code to make the thing that I need to show work, right? Like there's something else in between. Okay, I am going somewhere with this. We often think about time, cost, and resources is like only these things, right? You pick the 2. There's a whole big, broad band of things we have to think about when we're solving problems and the scope of that problem that we need to solve. So, pass 1. Pass 1 of trying to get this thing to work is a dev kit arrived, this one that was on the screen. I still had to figure out a whole bunch of stuff with an FPGA and integrate that and a bunch of other things. And the cool thing about this dev kit that arrived, this XMC from Infineon, is that it has an EtherCAT IP built into the core of the processor. So it's really easy to get to clock information. It was very cool. So it had the nerd factor going really high. So the board that's on the right is simply the physical board to handle being able to plug things in. The board on the left is the one with all the brain, and it has Ethernet and a bunch of other junk on it too, CAN and other things. So I've got this, and it has an EtherCAT label on it, which is really cool, but that's not super useful yet, right? So it ends up that Betkov is the company that does EtherCAT. They're the ones that thought of the idea. And if you're a member of the EDJ, you can just get what they call the slave stack code. It's basically, as they say, it's code written in ANSI. Exciting. And it's modular and simple structure enables fast entry into slave development. That sounded like exactly what I needed, right? And when you crack, it's one of those where you crack open the lid and you look at it a little bit and you're like, either you feel like you want to rewrite it or you want to just use it and not look again, right? No, the code is good. It's just it's in a style that we probably would look at and worry a lot about. How this works is you take an Excel spreadsheet file that describes the protocols and the bits and all that stuff about the communication for your device. You run it through a code generator, it spits out C code, and then you've got a bunch of other C code that you're going to go ahead and link against, and you might be tempted to compile it against a C++ compiler because that would be cool, except that you will first have to fix a lot of stuff because it just won't. It uses all the cool stuff in C, right, that we don't have in C++. That's a dig against C++, by the way. So eventually you end up with the SSC at the bottom, and you have these blocks around it. And the blocks are the things that you're gonna plug into. Examples, like when there's an interrupt, it would like to know about something. When it has information and it would like to tell you that it has received a packet, what does it do about that, right? And so these are all C pointers, pointers to pointers that you go ahead and say, this is the pointer to the thing I would like you to call at some point, at some location in the future. And the main loop. So there's you're gonna call in a main loop, this thing, that's one of the inputs. It provides a call for process data handling, interrupt controls, the interfaces to interrupts, and then the hardware concrete to the abstraction. So there is a abstraction level to hardware, right? There's like, I need to wiggle a pin, or I need to do a particular thing. And it would like to do that, and so it says, give me the function that is going to be the concrete portion of doing that thing. It's not that, it's a pretty nice interface, But it's in C, and I wanted to write my project not in C, right? And that's what we have to take care of. So here, we're just gonna worry about two things at the moment. This main loop is something I have to call in my main loop. So in my main loop, I'm gonna call the SSC's main loop. And when it has a cyclic data packet, some data to deliver, it wants to call a method, and we're gonna give it this process cycle to call. And it's gonna pass some pointers that will then do something with that data. So we're just gonna think about that as our interface. So let's talk about C++ just for a brief moment. We can overload functions. It's very cool, right? Like, I have func here, I have a null array, no, I have one that returns an int. I have a func that returns an int, I've got one that returns an int and takes an int, one takes a float, returns a float, one that takes two ints, a float, and returns a float. That's cool. So if we were to do this in C, we might be very cool and add single letters at the end of our func to help figure that out, right? And we wouldn't put an underscore there because that'd be too easy to read that way. So we would have these functions because we don't have overload sets, right? So can we use C++ functions in C? We've got, what the crowd is doing this like heads not up and down and it's not left and right. It's kind of, yeah, it depends upon what we mean by use, right? Yeah, so if we have overload sets, we have problems, right? How does the compiler figure out the overload set? What is it going to do? By the time this links, what's going to happen? Name mingling, right? The linker has to do something with this too, right? Everything along down the line is going to have to somehow figure out overload sets. So there's this thing called linkage properties. Function types, function names with external linkage, and variable names with external linkage all have a property associated with them called the linkage property. And that func1 down there, by default, things are external, right? They have external linkage. As soon as I say static, I'm saying that's it has internal linkage. As soon as I say that it has internal linkage, it no longer has a language linkage property associated with the thing anymore. So the idea of language link properties is that it allows us to tell a variety of different things, such as what are the calling conventions? What is name mingling like? What are different algorithms? Because it might be a different language. How do you deal with languages that aren't necessarily the language you're wanting? And C++ handles this with externc. So externc, we have externc++. There is a extern Fortran if you have the right extension, but there's only two that are approved, right? There's only two in the standard. And all that's doing, externc and externc++, is it's saying what the linkage property value is. It's associating something to that property as opposed to the default. So in my C code, if I have get radio ID, and in my C++ code, I want to use it, I have to tell my C++ compiler that the linkage property for this is C, so that it doesn't name mangle it, and so that it gets the calling convention right, if the calling convention is different. So those are the two things that we need to worry about. And if I want to call C code, this is how I do it, right? So externc C. If I want to go the other way around, and I have some C code that would like to, that I'd like to have that call and utilize something I've written in C++, it's the same type of thing. I have to then say that my C++ code has C linkage properties, so that it doesn't do name mangling, and so that it actually can then find it with the right calling convention. So I can still, with inside of that code, I can still call normal classes and use whatever I want as normal, but in this case, user loop itself, because it's externc C, will have no name mingling, and it'll have the proper calling convention. Does that make sense? All right. The other thing that I'm going to have to deal with is const in interfaces. And as opposed to having a whole bunch of slides about this, instead, if you are using these slides now, just click on the link at the bottom. Otherwise, go and watch this where Jason handles it just fairly recently, the const cast issue. He does not cover what do you do about third-party libraries. And that is a problem still. He gives the answer, he just doesn't call it out directly. And so take some time to watch that, because if you call something if you const cast away your const, and you call something that then mutates the values, you're in undefined behavior. And all kinds of badness will happen. So, he has some solutions. Check those out. All right. So, pass one. What does pass one look like? Pass one is like Michael is frantic about a whole bunch of things on the project, and we write some very ugly things that we won't put on a slide in case somebody would come back later and talk to me about it, right? And it's just like, let's just get this thing working. Let's integrate the C library with the C++ stuff. We have this process app that's going to be called by the C library. And so I have to externc C that. And I've been given this main loop from the library that I need to call on a regular basis. And so I externc C that, so that with inside of my normal loop, I can go ahead and call it the main loop that belongs to SSC. I'm going to take a moment here and just say that int main is really there. The bootloader and the startup code wanted an int main. So I got called out on a video a few years ago saying that I knew nothing about embedded programming because I was using examples with int main. I don't know. It just stood out. Okay, so it's not pretty. It's not pretty, but it worked, right? Like I just integrated it together. Nobody cares about pass one. But pass one is what you do so that you can like get to pass two. So if you've seen any of my talks where I talk about embedded stuff in particular, I talk about this a lot. We want to push the value up and the hardware spec stuff down. The value proposition of any project is what it does. The how it does it is almost always not important. Somebody else will figure that out later. The value is not typically in the how. Sometimes it is, but typically it's not in the how. So hardware-specific junk for vendor-purchased things is just, it's just hows, right? And we would like to push that down as far as we can in these divisions. Our goals in doing this is we want testability. We want the ability to simulate so that we don't always have to be running on hardware. We can actually do we can test our logic and make sure that our stuff is performing properly. And we want things to be more hardware agnostic. So our application portion would be at the top. Our hardware for A would be at the bottom. Maybe our hardware for B would be at the bottom. It ends up that this XMC board that we were buying, lo and behold, there is this like run on chips these days and nobody can buy stuff. And we suddenly had to buy 2 different things. It ended up that they had the same processor but different packages, which meant that the pins and a variety of other things weren't the same between the 2 exactly, right? The dies were different, caused us a little bit of, would have caused us a little bit of grief, except that by that point we'd already made it to this phase of how to develop. We want to be able to simulate our hardware so that we can run these things not always on hardware. And then when you're testing stuff, it'd be nice to not always be running on hardware too. So what does this look like now? What does main look like? Well, at the top, you'll see that I have this slushy app. We've changed names and modified a few things to protect the innocent. And it is being instantiated and specialized on this thing called XMC hardware. We'll look at that in a little bit. So I have app. Now my main loop looks like I'm going to init my app, call init on app. I'm still going to call main loop because that's, as far as I'm concerned, that's just this other library. Don't care about it. And then I'm going to call the apps loop because everything's loop. It's loops all the way down, right? Just main loops calling main loops. On the other side, the process, the data that came in, I'm going to do 2 things. One, I'm going to take the data that came in, and I'm going to convert that into something more reasonable, a format that I like a little bit better. And I'm going to call process cyclic data on the app. And then I'm going to say, what is the status? Does the app have any status that we should send back right now? And if so, what is it? Grab that and fill that back in. So I've kind of abstracted it away a little bit. It's not going to be great, but it's better than what we had before. So once I have this process app portion, this is getting called, this is the part that gets called kind of asynchronously in the system as things are happening. It's not necessarily controlled by the main loop. So this is the oddity inside of all of this. You can just think of it as like, this is the interrupt routine that occasionally like messes with you. I'm just going to grab that data and stick it in something much more reasonable as opposed to pointers to funky things with code-generated names, right? And so I'm going to grab that stuff, throw it inside of a struct, and now I have that in the struct. I do want to point this out. You can see I'm calling this toConfig in, and I'm passing it the PDO in, and I'm assigning that to config, right? That auto-config. Sometimes there's a lot of complaint about this, like, you just made a bunch of copies. You're causing all kinds of problems, right? There are no copies being made. And this is one of those where we want best practices. Best practices are inputs go in the argument list and return values are returned from functions. And so this will be guaranteed copy elision for the return with C++17. There's a paper that, if we name this, there's a paper that I think has been approved, will have named guaranteed elision. Okay, so there's no copies. So that's like the hardware level. Even though that's like main, that's just like, nobody cares about that stuff. So what else is inside the hardware level? Well, some type of hardware. I want to talk about this just for a moment. There are all kinds of different ways that you can abstract the hardware part. And there are all kinds of different approaches. And very often the approach is like, I'm going to abstract the bits, or I'm going to abstract the idea of interrupt registers or special function registers, something like that. Personally, I like to abstract much higher than that. And the semantics are higher than that. And the reason is a whole bunch of fold. But one is because I'm going to be able then to create simulators much more easily. I'm going to keep my business logic somewhere else and force myself to keep my business logic somewhere else. And just ask myself the questions of, what does the hardware provide to me? What is it that I'm really getting out of this? And so that init is just going to init something when init gets called. Tick, we don't really know what that does yet, but I'm guessing it probably gets called on the main loop, right? That probably is true. And we're going to be able to send stuff. on a CAN bus, and we're going to be able to get stuff back if there's something available off of the CAN. Some debug things. And then this is another place where I see a lot that people will abstract, like digital I/O. I want to be able to say that I have, I'm in idle, or I'm in operational mode, or I'm currently have an error, or I have a whatever. And instead, what I'll end up normally doing is just have something like this where I say status and idle. Status, clear error, gives me an idea of what the status is of a particular thing. And how do I respond to that? It can be very different depending upon what the target looks like. A simulated target would look very different than hardware. My main loop now looks like the init and the app loop. Yes?
Will the abstraction of the hardware vary a lot from app to app or problem to problem, depending on how you are using the hardware?
Well, the abstraction of the hardware, yes, the abstraction of the hardware will vary based, this is actually a great question. The abstraction of the hardware varies based upon the problem I'm solving, right? Okay, so the two ways of approaching the problem would be, I'm going to abstract the hardware. And then I just have like a generalized machine, and I'm always using a generalized machine. I just plug in new hardware all the time, right? The other side of the boat would say, let's not do that. What do I need to solve the problem at hand, and abstract that only? Don't abstract everything else. This is the same problem, by the way. I think as programmers we get in this problem all the time, which is we start abstracting things, or we start writing code in such a way where we go, oh, someday I might change that. Well, let me tell you, someday you will not change that, okay? You will do a whole lot of work, potentially, for something you will never change, right? And like, don't write setters and getters, for example. That's just like craziness. That's why that came around, that whole fad. Think about instead, when you're abstracting your hardware layer, what is it that I need from the hardware at a more of a semantic level than bit twiddling level? There will be bit twiddling below this. In fact, so I mentioned we had two different hardwares that we eventually had to deal with. This init function had to change based upon how the actual hardware pins for those masks were being initialized because of the two different die type we had. As well as the special function registers were in different spots, which was interesting. So there are things like that that occur. We ended up actually specializing hardware based upon, again, another thing. So this is another template parameter, and we just had some pins that were well-defined for the problem we were solving at hand. Okay, so we had a couple of these where we have it and the app loop, and we had this get cycle status and process cycle data. Those are our main things that we needed. And so as you can imagine, the app has those, and it doesn't really have a whole lot else that it needs to do. That's the interface at the application level. And then there's some private stuff we might have, like for example, process a new EtherCAT message, or I have a tendency to like to say, these are things that always happen before the loop, like set up to get loops working, and these are the things that happen after the loop is done, the main run loop, so I can just concentrate on the business logic in the middle. Okay, and then there are some things that we have for data members. And in particular, I want you to notice the data member at the bottom, because I don't think it would be a talk that I would have given, at least in the last few years, if we didn't have a boost SML state machine, right? So most of the work we want to somehow push into, I want to push it into a real state machine for realsies, because tons of stuff we do all the time are in state machines, and it's so much easier to reason than about the state machine, right? So we're going to push as much as we can into that state machine. I also want you to notice this, I left this on here because it's total code smell, right? There are things that are sitting here, in fact, it even has the word state in it, process EtherCAT state. It's either in waiting, have message, or invalid cycle. And that looks like it should be in the state machine, right? Yeah, okay. And had I taken one more pass at this, right, the next pass would have this inside of the state machine. It would not be this separate state that's living somewhere else. Okay. So hardware, or init just looks like, let's init the hardware that we have. And then our app loop simply checks to see what's going on. And then what I want you to notice is that it's calling the EtherCAT can state machine process event. So its whole purpose is just to create an object that it can then dispatch to the state machine to do the right thing. The case there with the have message is calling a fancier thing that just figures out again what just came in from EtherCAT of its message type and creates a real type out of that and passes that off to the state machine. So everything goes back to the state machine. And I think I don't want to talk about that right now. So, oh, but I do want to talk about this. So on the get status portion, one of the things that happens with that EtherCAT, right, is that on these cycles, you're getting potentially new information that you need to deal with. And it would be nice to send stuff back. So in this particular case, if I had a CAN message that came off of the CAN bus and I've got that available, it'd be really nice to send that back to the controller. It probably wants it. And so I asked the hardware layer, hey, do you have a CAN message? Is there something available? If there is, let's send that back. If not, then it does this next thing. And here's another code smell. So it gets, so one nice thing is like we have free cycles, right? So in EtherCAT, I don't have anything to send back. I might as well send something back. I have to send some, the data is going back one way or the other, right? So let's fill it up with something interesting. So let's go ahead and fill it up with some maybe debug status information. And one of the things that you see that I look for is, am I in the safety state? And if I'm in the safety state, then go ahead and send back the thing as an error. The lights are going off, which must mean I'm almost done, right? Is that something like that? Okay. So what do these state machine things look like? So the state machines are a struct, and again, I'm specializing on the hardware layer because the hardware layer has the abstraction that allows me to communicate to hardware and do what I want with hardware. And it has this operator callable that will allow me to get the state machine table back out with this make transition table. It's part of Boost SML. And it has a couple other things inside there. The thing I want to mention is, you can see at the bottom, I'm storing the hardware layer as a value, as if it's an instantiated object. And what's interesting about that, if you noticed earlier, right, it was just a wrapper, it's just a struct that has a bunch of static methods inside of it. And it has those static methods so that we can get to them based upon a type. There's no reason to make it into an object. Now, initially, you might say, well, I want to make it an object because I want to be able to store the state that's associated with it in there too. But at the hardware layer, you're going to find that actually creates more pain than help. Because now you're going to have to instantiate a singular object and pass that around all over the place, as opposed to I want to talk to the hardware layer. And the hardware layer will have its own objects that it's going to take care of. So here's our transition table. And the transition table itself is an abstraction written with a domain-specific language that allows us then to think about how do we transition from one state to the next and what happens in those transitions. We can think about the problems that we're solving at a really high level, right? Now, using BoostSML, we're allowed to actually just create states with strings through magic. And so I have my idle state, and if you have used UML state machine things, the notation looks a lot the same. And so if you're used to that notation, this notation for the DSL looks very similar. So the asterisk there is just like, that's the starting state. And then the event is some type. And the type itself then is what's going to cause the transition to occur, which may or may not have an action. And then it'll have a destination state. Where are we going to end up? If no destination state is mentioned, then it's an internal transition. We're staying within the state itself. You can see that we have guards. So down there somewhere a little bit in the middle, missing my pointer here, right here. We've got a guard. So it will only take that transition if the guard is true. Actions, and then the destination states. But events look just like, they're just types. We can have data associated with them, of course. And that would give us a payload then that we can be moving about. What do our guards look like? Guards are just callables. And at this point right now, if Chris was in the audience, he'd be going, why don't you use the dependency injection? Which is a really great question. And the reason that I didn't use dependency injection, I'm just showing you like raw stuff. Michael had to write it very quickly, right? Is because Michael at that moment couldn't remember how to use the dependency injection. And so the fastest way to get there was, I know I'm going to get the state machine as an object, as a reference. And so I can just ask it questions like, what is my current tick count? Okay, so if there were too many of these ticks, then I can return true, and then that will cause the guard to be satisfied, and it would take the transition associated with that. What do actions look like? Actions look like methods, again, that we can call. And again, instead of using DI, I'm just getting the state machine, which already knows about the hardware layer. So I got the state machine object instance. It knows about the hardware layer, and I can go ahead and just call, for example, send the can message object. So another nice thing about these hierarchical state machines is that they have entry and exit code for your states. So as you enter a state, it will execute whatever it is for the entry code. And as you exit the state, it'll execute whatever is the exit code. And so if you had a transition, like the ones that I had up here at the beginning, the top transition, up at the top, you can see that there are a variety of transitions that don't go to a state. They have no destination state. Those are internal transitions. They never exit the state, which means that exit code wouldn't be called and entry code wouldn't be called because it never left the idea of entry and exit code allows us to set something up that we really, like every time you arrive back into the idle state, you better be in this particular hardware state also. Things better be in a certain spot, as opposed to littering that around on transitions and possibly missing it when you come back in. So how we write that is we write it something like this. Enter idle would be our transition. And you can see then all of these things then in the table are set up such a way that I can just say, you can see the waiting message. We have the very last line for waiting message is an on entry. There's going to be an on entry method for that. And there's an on entry for safety. There's also an on entry for the idle. And then I can set that state back up into things that need to happen that might be important for that. Okay, so why do I push everything into state machines with nice transition tables? Because I can look at this table very quickly and see what did I miss? What didn't I handle? What event exists in the system that I didn't do something with? Am I sitting in a particular state and I didn't handle an event that might come in at any particular time? I did nothing with it. I mean, it would be nice to at least defer it and maybe handle it later. It allows me to reason about the state of my program in such a way that I can almost prove that at least the flow of it is proper. It's going to do the right thing. If you're doing, we've done a lot of medical devices over the years, and when you do medical devices, one of the things you got to try to prove to somebody is that it's going to do the right thing at the right time. And state machines allow you to do that. You can analyze each state that you're in and analyze whether or not you're doing a thing when an event occurs and whether it's proper for that state that you're in. So very powerful things. All right, so what was the next bit? The next bit were the protocols themselves, because protocols were very ugly. Like you just saw, I was grabbing stuff and shoving it in. It would have been really nice if that was more of a declarative type format. I've given plenty of talks on how to do that. And so it was taking then bit streams and changing those into kind of a declarative back and forth for the serialization. All right. What I hope you get out of our short little moment here is that when we approach problems, the problems are bigger very often, or our point of view should be bigger than perfect code. We're trying to solve some task at hand. And solving that task very often requires us to give up in other areas where we would want to be perfect, right? But you can iterate over it again and come back to it and make it a little bit better. And by using a few tools along the way, like starting to create code in which you are creating very clear layered abstractions and not mucking those up, allows you then to iterate over that concept that you have again and making improvements. Ben just gave an excellent talk about composition, and the ideas of composition play heavily into our ability to refactor and use things in a better way each time that we reapproach a problem. All right, totally out of time, I think. We've got time for one question, maybe two. Yes?
How do you deal with somebody sees it working because your first pass?
That's awesome. Yeah.
They want to just ship it out the door.
Yeah, somebody sees it working, first pass, and they want to ship it out the door. So a well-performed demo is indistinguishable from an actual product, right? That's the problem. And when you have an engineering hat on, that's a problem. But when you put the business hat on, that's what allowed your company to continue for another few months, right? And make the sale. So I'll tell you what we instruct our customers to do is to understand and realize the fact that what we're building right now enables the business to continue, but isn't the type of thing you want to ship to your customers, right? Being able to understand that, being able to tell that in words that the other person understands is the key, right? What are they worried about? They get a product, everybody hates it, and they get bad press, right? So it's like, this was great, it was a very good demo, it allows us to move on to the next stage, but you don't want to ship this stage because this stage will be bad press, right?
I have more of a comment.
Yeah.
At the beginning you said that writing throwaway code. It didn't look like you were writing throwaway code. It's just a regular iterative approach.
Sure.
And, without that feedback, you don't know what proper abstraction.
Yeah, that's.
So you're not throwing away code. You're on the journey to the destination. And I also think just on that last question, where a really good demo, you can usually say to the customer, it's limited in some form, right? So you're not going to ship it right now because you can say it's more people.
Yeah. Okay.
You get the proof of concept of the volume, which allows you to
Yeah.
survive the next.
That's right. Yeah. Great comment. So two comments. The first was that doesn't look like throwaway code. It looked like more iterative. That first thing that was so ugly I didn't put on the thing. I guess we could have called that iterative if we were being really kind and called it like exploratory how the chip worked. But it all got thrown away pretty much, yeah. And then the second point, which was really great, is that describing it as buy-in, I think is what you said. Yeah, the demo, the well-performing demo does what it needs to do, which is to get you to the next funding phase or whatever it is that you're working on for that particular thing. Yeah. Anything else? Yes. Yeah. Yeah, so okay, so the question is about boostless ML and the atrocious compiler errors if you do something wrong. Is that basically? Yeah. And unfortunately, the end result for you was that maybe while you were able to work through those errors, other people were having trouble figuring out what it meant. This, by the way, is not unique to boostless ML. It's like anything that's a domain-specific language, Spirit, all these different things are just going to cause pages and pages of errors for you to work through. And I think the best way with DSLs to deal with it is you work small and you just keep adding to it, right? Don't sit down and add everything in the whole world. On the flip side with SML, I literally add all of my table immediately because I'm thinking about the table. That's what I'm really thinking about. But then when I go back and I actually want to compile it, I start smaller personally. It ends up that there are quite a few people here who use SML, might have some other ways that they approach it. As I look at the front row here. Yeah, that's I was afraid that was going to be the answer. The answer was they have access to the author. Yeah, so if you... Yeah. Yeah. The only way I know around that problem is to build smaller. Don't build large. Like start small and then keep building on top of that and building on top of that. You'll see, like it's on almost all my slides, right? I'm a huge user of it because the value of it far outweighs the pain of the compiler when I make a mistake. And yeah, I have to make it through whatever that is that I did. Yeah, it has really great Emacs support because of bin, actually. I adopted bin's entire .emacs file simply so I could get that support. Okay. Yeah, so the other comment is newer compilers are going to be able to give you better results, better output. And if you're on an older system, maybe there's a trick you all already use. Compile against something newer, right? So that you can get decent messages out. Yeah. Well, maybe we can go talk to Chris later. We'll ask him what he does. Anything else? All right. Well, thank you for your time. I appreciate it.